This fluid mechanical dissection video will discuss the Flettner rotor. As seen in images below, Flettner rotor sails can be seen on ships where they are a common occurrence in order to improve fuel efficiency and on planes as a substitute for wings. The basic principle behind a Flettner rotor is that the rotating cylinders can utilize free-flowing velocity streams to provide a net pressure force perpendicular to the flow of the air around it. The main mathematical condition for irrotational flow is that the vorticity must be zero. The stream function can be further defined as a scalar represented either in integral form or more commonly as an equation whose partial derivatives must be the 2D velocity vectors. Using this, we can relate irrotational flow to the Laplace equation. Solving this, partial differential equations yield three main equations, the vortex, source, and doublet equations. For our model, the doublet equation defines the cylindrical boundary of the Flettner rotor, while the vortex equation alters the streamlines around the cylinder based on the circulation or rotation rate of the cylinder. Using Bernoulli's equation to the volume around the cylinder, which applies if viscosity is neglected, shows that there is an increase in velocity over the top of the cylinder, which means that there is a decrease in pressure compared to downstream. This means that there must be a subsequent increase in pressure over the bottom portion. It is this pressure differential that allows the Flettner rotor to be used as a system of propulsion. The key takeaway is that the irrotational model accurately predicts a lift force is created by the Flettner rotor.
For the Flettner rotor and rotating cylinders in general, irrotational flow analysis is not enough to properly predict the fluid flow everywhere. To understand how the fluid near the wall behaves and how that plays into drag, we also need to use boundary layer analysis. This is the boundary layer equation, and this specific term allows us to predict the velocity distributions of the fluid along the surface of the rotor that are caused by the pressure gradients predicted by the irrotational flow analysis. Most notably, the boundary layer analysis predicts that towards the back of the rotor, the velocity profile reverses direction. This is because there is an adverse pressure gradient that's pushing back on the fluid, and the fluid near the surface doesn't have enough momentum to fight through it, which causes the flow to separate. The separation of flow near the back of the rotor causes unsteady and turbulent flow, which in turn results in drag. This is one of the main reasons we don't see airplanes with rotor wings, because they generate a lot more drag than an airfoil would. Since the separation of fluid flow is coincident with drag, anything that will push the separation points further downstream will reduce the drag.
Depending on both the Reynolds number of the fluid, the velocity ratio gamma, and the surface roughness, the lift force generated by the rotor can greatly differ from what the irrotational analysis predicts. In an irrotational model, lift on the Flettner rotor is solely a function of the cylinder's radius, length, rotational speed, and the free stream fluid density and velocity. It is often represented using the lift coefficient. In the irrotational model, the lift coefficient is linearly proportional to gamma. However, experimentally, this relation follows a more complex trend. In instances where significant fluid separation occurs, the contribution towards lift upstream of the separation point can still be computed using an irrotational analysis, while downstream, the asymmetry of the separation points must now also be considered. The lift and drag of a Flettner rotor quickly becomes multidimensional, as both are influenced by the surface roughness, the Reynolds number, and the velocity ratio. For high Reynolds number flow, this analysis is so complex that it cannot be computed numerically. Test setups must instead be used to derive lift and drag coefficients at different experimental conditions. Currently, the influence of the velocity ratio on Flettner rotors through high Reynolds number flow is just starting to be more rigorously tested, while the influence of differing surface roughness in such conditions has continued to receive very little experimentation. Surface finish has primarily been investigated for unrotating cylinders, showing that depending on the rotor surface finish, a drag crisis can occur at different Reynolds numbers. Flettner rotors have seen very little use in real-world applications, most notably is on shipping vessels. In this instance, lift on the rotor is in the direction of the vessel's velocity, providing a forward thrust. This is because the motion of the fluid is primarily from a crosswind, rather than as a result of relative motion of the air due to the boat's forward velocity, like it would be in the case for a plane. For this application, the fluid's Reynolds number is on the order of 10 to the 6, and so the effects of surface roughness and velocity ratio are best determined experimentally. We reached out to Norse Power, the leading company in the nautical Flettner rotor industry, to ask why a smooth surface finish was preferred for this specific application. The choice boils down to a simplification of the manufacturing process rather than an optimization of lift and drag characteristics.
The end plate on a Flettner rotor helps the fluid flow to remain in 2D so that the pressure difference across the length of the Flettner rotor doesn't change. If there weren't end plates, then the flow near the ends of the cylinder would want to go over the cylinder rather than past it, which would create less lift according to the irrotational flow model. By adding end plates, the flow is more restricted, which in turn helps create more lift.